Welcome. Today we're diving into the periodic table, the ultimate map of all known chemical elements. Whether you're a student, a science enthusiast, or just curious, this one-shot guide will help you understand how the periodic table is organized and why it's so important. We'll explore its layout, the meaning behind its rows and columns, and how it helps us predict the properties of elements. Let's start our journey by looking at the big picture. What exactly is the periodic table, and how did it come to be the backbone of chemistry? Periodic table wasn't always as complete as it is today. In the 19th century, scientists like Dmitri Mendeleev noticed patterns among the elements and arranged them in a table based on their atomic weights. This clever organization allowed them to predict the existence and properties of elements that hadn't even been discovered yet. Over time, as more elements were found and atomic theory advanced, the table was updated to reflect new knowledge. Today, it's a living document, still growing as new elements are synthesized in labs. Periodic table is organized into rows called periods and columns called groups. Each element is placed according to its atomic number, which is the number of protons in its nucleus. The table shape isn't random. It reflects recurring patterns in element properties. For example, elements in the same group often behave similarly in chemical reactions. Understanding the structure helps chemists predict how elements will interact, making the table a powerful tool for science and industry. Every element has a unique atomic number, which tells us how many protons are in its nucleus. This number is the key to an element's identity. Change the number of protons and you have a different element. For example, hydrogen has 1 proton, so its atomic number is 1. Helium has 2 protons, so its atomic number is 2. This simple counting system is the foundation of the periodic table's order and helps us understand the relationships between elements. Columns in the periodic table are called groups or families. Elements in the same group share similar chemical properties because they have the same number of electrons in their outer shell. For instance, all elements in group 1 are called alkali metals and are highly reactive, especially with water. Group 17 elements known as halogens are also very reactive. Recognizing these families helps chemists predict how elements will behave in reaction. Rows in the periodic table are called periods. As you move from left to right across a period, the atomic number increases by 1 with each element. This progression leads to changes in properties like increasing electronegativity and decreasing atomic radius. These trends are key for understanding why elements behave the way they do, and they help chemists predict the outcomes of chemical reactions. Periodic table is often color-coded to show which elements are metals, nonmetals, or metalloids. Metals found on the left and center are shiny, conductive, and malleable. Nonmetals on the right are more likely to be gases or brittle solids and are poor conductors. Metalloids found along the zigzag line have properties in between. This classification helps us quickly understand what to expect from each element. Group 1 elements are called alkali metals. These include lithium, sodium, potassium, and others. They're soft, silvery metals that react explosively with water. Because they have just 1 electron in their outer shell, they're eager to lose it and form positive ions. Alkali metals are used in batteries, medicine, and even fireworks. Their high reactivity means they're always stored under oil or in special containers. Group 2 elements are the alkaline earth metals like magnesium and calcium. These metals are harder and less reactive than alkali metals, but they still react with water, though more slowly. They're important for life. Calcium is crucial for bones, and magnesium is vital for plants. Alkaline earth metals are also used in fireworks, construction, and medicine. Large block in the center of the table is made up of transition metals, including iron, copper, and gold. These elements are known for their strength, conductivity, and colorful compounds. Transition metals are used in construction, electronics, jewelry, and even as catalysts in chemical reactions. Their unique ability to form various ions makes them incredibly versatile in both nature and industry. Just to the right of the transition metals, you'll find the post-transition metals like aluminum, tin, and lead. These elements are softer and have lower melting points than transition metals. They're widely used in packaging, construction, and electronics. Aluminum, for example, is lightweight and corrosion-resistant, making it perfect for cans and airplanes. Metalloids such as silicon and boron sit along the zigzag line between metals and nonmetals. They have properties of both groups, making them essential in technology. Silicon, for example, is the backbone of the computer chip industry. Metalloids are often semiconductors, meaning they conduct electricity under certain conditions, which is key for electronics. Nonmetals are found on the right side of the table. These elements, like oxygen, nitrogen, and carbon, are essential for life. They're usually gases or brittle solids and don't conduct electricity well. Nonmetals play crucial roles in biology, the atmosphere, and industry. For example, oxygen is vital for breathing, and nitrogen makes up most of the air we breathe. Group 17 elements are called halogens, including fluorine, chlorine, bromine, and iodine. These are highly reactive nonmetals, often forming salts when combined with metals. Halogens are used in disinfectants, lighting, and even in medicine. Their reactivity makes them dangerous in pure form but incredibly useful in compounds. Group 18 elements are the noble gases like helium, neon, and argon. These elements are colorless, odorless, and extremely unreactive. Because their outer electron shells are full, they rarely form compounds. Noble gases are used in lighting, welding, and even in balloons. Their stability makes them unique among the elements. Lanthanides are a series of 15 elements found at the bottom of the periodic table. They're sometimes called rare earth elements and are used in magnets, lasers, and electronics. Lanthanides are known for their similar properties and are often found together in nature. They play a vital role in modern technology, especially in green energy and high-tech devices. Below the lanthanides, you'll find the actinides, including uranium and plutonium. These elements are radioactive and are used in nuclear power and medicine. Actinides are rare and often unstable, but their unique properties make them important for energy production and scientific research. Hydrogen sits at the top of the periodic table, but it doesn't quite fit with any group. It's the lightest element and the most abundant in the universe. Hydrogen is a gas at room temperature and is used in fuel cells industry and even in stars. Its unique properties make it a special case in chemistry. Helium is the second element and is famous for making balloons float. It's a noble gas, so it doesn't react with other elements. Helium is also used in cooling superconducting magnets and in deep-sea diving. Its low density and inertness make it valuable for many applications. Carbon is the backbone of all living things. It can form long chains and rings, making it incredibly versatile. Carbon is found in everything from diamonds to graphite to the molecules in our bodies. Its ability to bond with many elements makes it the foundation of organic chemistry. Oxygen is vital for breathing and is the most abundant element in the Earth's crust. It supports combustion and is found in water, rocks, and living organisms. Oxygen's reactivity makes it essential for life and industry, from respiration to steelmaking. Nitrogen makes up about 78% of the air we breathe. It's a colorless, odorless gas that's essential for life. Nitrogen is used in fertilizers, explosives, and even in food packaging. Its stability as a gas makes it a key component of our atmosphere. Sodium is a soft, silvery metal found in table salt. It reacts violently with water and is essential for nerve function in our bodies. Sodium compounds are used in everything from soap to streetlights. Its high reactivity means it's never found pure in nature. Magnesium is a lightweight metal used in airplanes, fireworks, and even in our bodies. It burns with a bright white flame and is essential for plant photosynthesis. Magnesium's strength and low density make it valuable for many industries. Aluminum is everywhere, from soda cans to airplanes. It's lightweight, corrosion-resistant, and easy to shape. Aluminum is the most abundant metal in the Earth's crust and is used in packaging, transportation, and construction. Silicon is a metalloid crucial for modern technology. It's the main component of computer chips and solar panels. Silicon is also found in sand and glass. Its ability to conduct electricity under certain conditions makes it perfect for electronics. Phosphorus is essential for life, found in DNA and bones. It glows in the dark and is used in fertilizers, detergents, and matches. Phosphorus is highly reactive and never found free in nature. Its compounds are vital for energy transfer in cells. Sulfur is a yellow, nonmetallic element known for its strong smell. It's used in fertilizers, gunpowder, and medicines. Sulfur is essential for life and is found in proteins. Its unique properties make it important in industry and biology. Chlorine is a greenish-yellow gas used to disinfect water and in making plastics. It's highly reactive and dangerous in pure form, but its compounds are essential for modern life. Chlorine is found in table salt and is used in cleaning products worldwide. Iron is a strong, magnetic metal used in construction, tools, and our bodies. It's the main component of steel and is essential for carrying oxygen in blood. Iron's abundance and strength make it one of the most important industrial metals. Copper is a reddish metal known for its excellent conductivity. It's used in electrical wiring, plumbing, and coins. Copper's ability to conduct electricity and resist corrosion makes it vital for modern infrastructure. Zinc is used to protect other metals from rusting, especially in galvanized steel. It's also important for our health, found in many enzymes. Zinc's resistance to corrosion makes it valuable in construction and manufacturing. Silver is a precious metal known for its shine and conductivity. It's used in jewelry, electronics, and photography. Silver's antibacterial properties also make it useful in medicine. Its rarity and beauty have made it valuable for centuries. Gold is famous for its beauty and resistance to tarnish. It's used in jewelry, electronics, and as a store of value. Gold's rarity and unique properties have made it a symbol of wealth and power throughout history. Mercury is the only metal that's liquid at room temperature. It's used in thermometers, switches, and some industrial processes. Mercury is toxic, so its use is carefully controlled. Its unique properties make it fascinating but dangerous. Lead is a dense, soft metal used in batteries, shielding, and old pipes. It's toxic, so its use is now limited. Lead's heaviness makes it good for blocking radiation, but its health risks mean we use safer alternatives today. Uranium is a radioactive metal used as fuel in nuclear reactors. It's also found in some types of glass and military applications. Uranium's ability to release energy through fission makes it a key element for nuclear power and research. Plutonium is another radioactive element used in nuclear weapons and reactors. It's highly toxic and must be handled with extreme care. Plutonium's powerful energy release has made it both a source of power and controversy. Some elements on the periodic table don't occur naturally, they're made in laboratories. These synthetic elements like technetium and einsteinium are often unstable and radioactive. Scientists create them to study nuclear reactions and the limits of atomic structure. The periodic table reveals trends in element properties such as atomic size, ionization energy, and electronegativity. These trends help chemists predict how elements will react and combine. For example, elements become more metallic as you move down a group and more nonmetallic as you move across a period. Each element's position on the table tells us about its electron configuration, the arrangement of electrons around its nucleus. This configuration determines how an element reacts with others. Understanding electron configuration is key to mastering chemistry. Valence electrons are the electrons in the outermost shell of an atom. They play a crucial role in chemical bonding and reactions. Elements in the same group have the same number of valence electrons, which explains their similar properties. Elements combine to form compounds through chemical bonds. The periodic table helps us predict which elements will bond and how. Ionic bonds form between metals and nonmetals, while covalent bonds form between nonmetals. Understanding these bonds is essential for chemistry. The periodic table isn't just for scientists, it's used in classrooms, industries, and research labs worldwide. It helps us discover new materials, develop medicines, and understand the world around us. Its organization makes it a universal language for chemistry. Periodic table is more than a chart, it's a powerful tool that unlocks the secrets of matter. By understanding its structure and the properties of elements, we can predict reactions, create new materials, and explore the universe. Whether you're studying for a test or just curious, the periodic table is your gateway to the world of chemistry. Thanks for joining this one-shot journey through the elements.